All right, let's take a look at an example of an application question where we're going to be addressing the average rate of change as well as the instantaneous rate of change. So the motion of an avalanche is described by the function s of t is equal to 3t squared, where s of t is the distance in meters traveled by the leading edge of snow after t seconds. We want to find the average speed from 0 to 5 seconds, and for part 2 we want to find the instantaneous rate of change at 10 seconds, right? So in this case, we have something called the position function, s of t, right? And the position function just tells us the location of an object after a certain amount of time that's passed, right? And the position is usually in some kind of length dimension, that could be measured in meters or centimeters, kilometers, etc., right? Now, the rate of change of a position function gives us a type of velocity function, right? And the two types of velocity functions we're going to be looking at is the average speed or velocity and the instantaneous speed or velocity. Okay, so those are really the two different cases, right? And velocity is basically speed, but you also incorporate a direction, right? So we can look at this as speed for the time being. Now, anyways, for the average speed from 0 to 5 seconds, we're basically using the slope of a secant. So we know that the slope of a secant from a previous lesson is f of x2 minus f of x1 divided by x2 minus x1, right? And let's call it x2 5, it's the upper limit, and x1 is 0, it's the lower limit. And in this case, f of x2, or f of 5 here, is basically 3 times 5 squared, which is basically 3 times 25, which is 75. Okay, so at 5 seconds, you're basically a position 75 meters away from some reference point, right? So f of 0 here is basically 3 times 0 squared, which is 0. Okay, so initially you're right at the reference point. And if we look at the slope of the secant, it's basically 75 minus 0 over x2, which is 5, minus 0, and that's going to give us 75 over 5, which is basically 15. Now you can notice here that the numerator here is in meters and the denominator here is in seconds, so that's why we get the unit meters per second. Okay, so that's your average speed from 0 to 5 seconds, right? So that's your average speed, that's part 1. But we also need to look at the instantaneous rate of change at 10 seconds, right? So if we're looking at the instantaneous rate of change, we need to find the slope of the tangent. And in this scenario, I'm going to look at using the first principle. Okay, now you could also use a small interval if you need to. Okay, but I'm just going to use the first principle method to do this. Okay, you guys can practice using other methods, and you should see the same answer. Once again, they are approximations, right? So if I use the first principle method, I am creating an instantaneous rate of change function, f prime of x, which is basically the limit as h approaches 0, f of x plus h minus f of x over h. Okay, so let's look at, in this case, instead of thinking about x, you can think about it as t, right? So I'm going to do, first I'm going to look at f of t plus h, which is basically 3t plus h squared, right? I'm going to expand this guy like a plus b squared. You're going to get a squared plus 2ab plus b squared. All right, so if I expand this guy out, you get 3 times t squared plus 2th plus h squared. And you get 3t squared plus 6th plus 3h squared. Okay, now I have this, and then I'm going to also look at my negative f of t instead of x, right, which is basically negative 3t squared. And if I combine this, f of t plus h minus f of t, you're going to get 3t squared plus 6th plus 3h squared minus 3t squared. All right, so you can see that these are like terms that cancel out, and you basically are left with 6th plus 3h squared. You can notice that there is an h that's common, so if I factor this out, you get 6t plus 3h. And this is where the limit is h approaches 0, and we can see that the h's cancel out. And now at this point, I can let t equals 0. Whoops, I can let h equals 0. Sorry about that. Okay, let h equals 0. If I let h equal 0, we can see that our instantaneous rate of change function, f prime of t here, is going to look like that h would just cancel out, right? 6t plus 3h cancels out, and you get 6t. Okay. And if it's 6t, and we want to figure out the instantaneous rate of change at 10 seconds, we're just doing f prime of 10, which is 6 times 10, which is 60 meters per second. Okay? So remember that this is at a single instant of time, the instantaneous rate of change, and the first scenario was the average rate of change between a time interval from 0 to 5 seconds. Okay, I hope you guys can understand the difference between the two.